So in this video, we're going to take a look at graphing ln x, which is a special case of a logarithm that has a base of e. So let's start with what is e. If you remember, e is approximately equal to 2.718 repeated in an irrational fashion, similar to pi. It's a universal constant that's used in math and finance and even accounting potentially, and physics and chemistry and other science classes. And so it's important to kind of have exposure to this in a class that leads to a college level class. And so remember, this just means log base e, but we would never write that down. We would write ln instead. But the reason is these key points, the reason this is important is these key points are going to follow the exact same process as earlier, meaning here we have -1 with 1 over b. So b would be e, so it'd be 1 over e. Here we always have the base number for logarithms, just is 1, 0, the x-intercept. And then here we have base comma 1, which the base would be e. So when we graph these, it's important to remember to always graph the asymptote. So our asymptote is going to be, just like any normal logarithm, it will be the y-axis for x equals 0 right there. And then our graph of these points will be in the same shape, right? So 1 over e is about a third-ish. So 1/3 -1, 1, 0 for every logarithm, and then 2.8 comma 1, 2.718 comma 1. And so we get this typical form that we've seen, looks just like that. Not a lot changes, right? So our asymptote is still going to be x equals 0. Our x-intercept is still 1 comma 0. Our y-intercept is none. Now, remember, these are dependent upon transformations and translations. They can be other things. That's just the base graph. The base graph of E is a growth graph. The end behavior is to state the domain, which is the exact same for any logarithm, 0 to infinity. And then take a look at what's happening in the y direction. As it goes to 0, the graph goes down to -infinity, that part of the range. And then as the graph goes to infinity, the graph is going to go up to infinity, very slowly, mind you. Okay. Log base 10 of a million is only 6. So it happens very slowly. All right, so let's take a look at a transformational problem of this. So key points are going to change. They're still going to be the same. 1 over e, -1, 1, 0 in e, comma 1. Our asymptote will still be here, but it's going to move, in this case, to -1. Let's see why. I always like to start with the asymptote. It's right there, and it's telling me that the h value is equal to -1, making our asymptote x equals -1. Then I like to put the key points on, and the reason is because these key points are going to approach this asymptote, so it just gives you a ballpark of where you need to be. So 1/3 -1, 1, 0, and 2.718, and then we're going to go back to our transformations. They tell us to move the graph left 1 and down 2. So if I take a look over here, left 1 down 2, left 1 down 2, and left 1 down 2, and that'll give us a nice similar graph to the original but transformed version. And we can very clearly see that the y-intercept this time, again, is -2 comma 0. I know I just said that it's typically none, but I did mention that it can transform to something. And so why is that going to be transformed to -2 comma 0? Let's take a look at the algebra. It's always good to look at algebra. So that would be ln of 0 minus 1, right? And then, sorry, 0 plus 1, and then -2. Well, that would give you ln of 1 minus 2, and this goes to 0. Why? Remember, logarithm is the inverse of an exponential, and the base is e. The answer is 1. So what did we raise it to? The 0. ln of 1 is 0, just like e to the 0 is 1. And that would, of course, give us the answer, -2, which you're seeing on the graph right there. So what is the x-intercept? Well, the x-intercept is going to take some algebraic stuff. So let's go do it over here. We set it equal to 0, and we solve. Make sure you write it down correctly. Number one error is simply transposing the problem wrong. We're going to add 2 to both sides, giving us 2. And then to get rid of ln, we are going to raise it to the base, commonly called e'ing it. So we eat it to cancel the base, giving us e squared. Do not turn that into a decimal. It actually makes it worse. Then you just subtract 1 on both sides. And yeah, your answer is a weird, believe it or not, common answer when you get to higher level math, physics, financial equations. You get answers like e squared minus 1. And I'll show you in a minute on Desmos that that is in fact the x-intercept way over here. This is still growth. Nothing reflected it to make it decay. The end behavior is as x goes to -1, the asymptote is the beginning of it. And then after it goes to -1, the graph's domain will end at infinity. And then the graph itself at -1 is going down to negative infinity, and the graph itself, as it goes to infinity, is going to infinity. So at -1 on the x-axis, the y-axis is going to negative infinity, and at infinity, the graph is still going to infinity, just very slowly. So here is that graph on Desmos. Okay, so it looks very similar to what we have. You can see the y-intercept very clearly, the asymptote at -1. You can see that we don't know where this is. If I scroll over, it comes out to this decimal. And then I typed e squared minus 1 into the Desmos, and you can see it's the exact same decimal. Keep in mind, on a test, on an assessment, you're going to need to know this weird version. Even if you know the decimal version, you're still going to need to be able to solve it. All right, so that's LN. Next video, we're going to look at how to take a graph and figure out what we did for the transformation.